All right, folks, let's start. Hello, everyone. This is Dr. Yuzo. This is ECE 360 in Control System class. Today is our 20th lecture, and according to the Gantt chart, we will keep talking about the design via the Locus. And also today, we're going to do the review for the upcoming midterm 3, okay, which is next Monday. And this Wednesday is also important since we are going to assign the project. Okay, and the project content is closely related to today's lecture as well as the next Wednesday lecture. Okay, we will have MATLAB-based design procedure be initiated. So keep up and have any questions, let me know. Okay, so let's move on. Well, of course, can you guys hear me well? Anyways, this is a little bit review of what we learned from last lecture. We learned the P controller and the PI controller, right? We talked about them. The P controller, what P controller can do to a original Locus. This is something you need to understand. In other words, given a original system, or we call it uncompensated system, okay, without giving any controller yet, okay, original system. If you add a P controller itself, which is nothing but a gain, right? And right in front of the plant, the P controller, adding a P controller, what can this controller do to the original system, PH, right? They're saying the P controller won't be able to change the Locus. The Locus looks exactly the same. However, what can it do further? It can push your original system closed loop pole location to push it moving along the Locus, right? So you will have different location of the closed loop poles. Okay, that's the effect of the P controller itself. Right? And what else P controller can do? A P controller can change the stability. Right? So from here, as the example we had, the original low closed loop poles are at red. After adding P, it pushed to the blue. Comparing to the red location, the blue location closed loop poles, the system has what? Worse stability, right? Because it's closer to the imaginary axis. So this stability is harmed. Right? So this is what can P controller do to the original system. Okay. Next, we learned the PI controller. PI controller obviously can do more. First, PI controller is introducing a gain. Besides of gain, it's introducing 1, 0. It's 1, 0. Right? With any value depending on your Ki and Kp value designing. Right? And also, it's introducing a 1, 0 pole. Okay, pole 0. This 0 pole is very significant since it is adding the system type by 1. Therefore, the system gonna become immune to the step input response status error. No step input status error, okay, not at all. As long as you're applying PI controller, you can achieve that. Of course, you can imagine also by properly designing Ki and Kp value, you will be able to change the transient, improve the transient as well. Okay. So this is the one thing the PI controller can do. Okay, this is one thing. Another thing PI controller can do is this. Okay. Maybe you verify this later, but now just second bulletin here. The PI controller can do what? If the 0, which is this guy, right? Negative Ki over Kp. Here, 0. If the 0 of PI controller is designed close to origin point, PI can keep the original locus without big change. Yeah, maybe the reason is a little bit blurred, but how about the description here? Is it clear? Talking about. So if you designing the PI controllers 0, close to origin point, which is 0, is close to 0, then your PI controller won't change the original locus a lot. Basically, keep it. Of course, no way to be exactly same. Okay, no way to be exactly same, but you can keep it roughly. It won't change too much. That's what does it mean. Okay. So PI controller can basically do these two things. Basically, keep the original locus and also make the steady error for input of step 0. Right? This is the PI controller, and now what we want to do is really go through an example to see how we use the MATLAB to find host location, find the gain location, and do some design work as well. Okay. Very, very important. Example 1. The MATLAB code will be posted into Canvas after today's lecture, but during the lecture, you want to focus on listening and understanding how it works, this procedure, okay? So this is a module 7, example 1. Okay. Very important. First of all, giving you a original system, obviously, a given system. We call, once again, the original system as uncompensated system. We call the system with design controller as compensated system. Okay? Become familiar with these two terms. Okay? So uncompensated system is given as this. This block diagram, very helpful for us to visualize the system. Okay? Even a system like this. There is something I need to clarify it as first place. So by looking at this given system, is what's the order of the system? Anyone tell? What's the order of the system? Or say how to tell the system order? No, we are not talking about system type. We are talking about system order. Therefore, Noah is right. Very good. Okay. System order, not system type, is what? 3. Oh, by the way, how can we tell this? How can we tell this number? What's the reason is 3? Order of denominator. Very good. Order of denominator of whom? Whose denominator? Feed forward only? Nope. No. Feed forward transfer function or open loop transfer function cannot tell us the system order. Here we go. Closed loop transfer function. Denominator order is the system order. This is something we learned back in module 1 or module 2. Be very careful. Once again, I'm asking the system order, not system type. Okay, system type, yes, is 0. Yeah, system type 0, no problem. System order, is up to the closed loop transfer function denominator polynomial. Does it make sense? First of all, okay, this concept need to be clear. Okay, this concept need to be clear. Okay. After this, let's think about one question. Okay, this is a third order system, right? Which means it's basically higher order system, actually, right? But we are going to use second order system knowledge to do the design work. And this was one of the questions from Sawyer. I don't know if anyone here remember. He ever asked, well, your given system is not necessarily second order system. How can you use like these things? Remember those PS, TP, overshoot? They all in terms of what? Real parts and imaginary parts of second order system closed loop pose, right? Does it make sense? Remember these things? Okay. His question back then was, well, the given system is not really a second order system. However, these conclusions, or say these formula, are all about second order system. Well, how can we apply them? It was a very good question. Okay. But back then, I said, well, I'll leave it to module 6 or 7 to explain. So here I need to clarify now before we are going further, because this given system obviously is not second order system anymore. And the final project given system is not second order system either. Okay. However, we're gonna keep using these second order system conclusion here. Okay. The reason is here, and this is called pose, dominant pose rule. What this is talking about? What it's talking about is under certain condition, a system with more than 2 poles or 0 can be approximated. Yeah, this word is very important. It tells a lot, right? It tells a lot. Not accurate, but approximated as a second order system with 2 complex conjugate poles. And that 2 complex conjugate poles are nothing called the dominant poles. So pretty much we are approximating a higher order system into a second order system. Therefore, we are focusing on that 2 dominant poles only. This is how we deal with the higher order system. Does it make some sense? And of course, what's the key? The key is what is that a certain condition, right? Obviously, this is a constraint. This is very extremely important. In other words, not every single higher order system can be approximated, right? And not every one of them. No, you need to meet certain condition. Therefore, what is the certain condition then? What is certain condition? What is it? a certain condition, if we describe it, is like this. So other poles must be much further than the dominant pole to the origin point. And this is the description, but let's be real. What does this mean? I'm giving you two examples. Okay, two examples. You can tell one of them is something we are able to approximate to second order system. The other one is not. Okay, so the first one you're seeing, we have two poles, two complex conjugate poles, and we have an interpose, which means obviously third order system, right? Interpose is here. Inner system, we have two complex poles, and third pole is over here. So according to this description here, which one? Say we call it 1 and 2, system 1 and 2. So which one we are able to approximate it to second order system? Which one? 1 or 2? Obviously 1, right? Obviously 1. Okay. This one, check. This one, no. But the reason is this one meets the so-called certain condition. This one doesn't. What does it mean? The other poles, well, we are assuming there's only one so-called other pole, right? It's far away from origin point comparing to the two complex poles. But to this case, what do you see? With your third pole here is too close comparing to the two complex poles, to the origin point. So this one, if you do the approximations, what's going to happen? The step response going to be off by a lot. In other words, you're using these two poles only to do the design, and then the step response is going to be off from the original system a lot. However, here, you only use these two dominant poles to do the design. The resulted step response, as well as the future frequency response, won't be off by a lot. And that's the so-called you can or cannot approximate them to second order system. Here, John is asking, what does further than mean numerically? Well, the textbook is given the definition, if I remember correctly, like if the pose is 5 times further than the dominant two poles, then you are able to do this approximation. The textbook's definition or description is like this. However, I don't like such kind of description very much, because following that, I thought some system approximation is not accurate enough. That's why I'm using much further. I agree. This is not numerically exactly precisely description. I understand that. I fully agree. However, much further. And the textbook using 5 times, or I don't think it's 10 times. I remember it's 5 times, but I don't like that. It's not working very well. All right. Of course, the following question should be, well, how can you know if you can, right? You know that, right? Who can answer this question? How can you know, can you or can you not? How can you fairly tell that then? The question says so. Well, let me say it in this way. In this course, okay, in this course, in especially the assessment and in the exam, we will always assume we are able to do this approximation. Okay, if you're free to apply the second order system, these things, if you're free to apply these things, okay, if you're free to use only two dominant poles in this course, no problem. Okay. I'm not planning to give you an exception for it. Okay. In this course, if you relax, no, we are definitely fine. However, make it more generalized case. That's how can we tell? How can we really tell, fairly tell, or at least whether the system could be approximated or not? How? Anyone knows?
Could you compare the root locus of both and see how far it's off?
That's yes. By that you can tell how far it is. Absolutely, you can. However, the thing is, after knowing how far, you probably still cannot tell if whether you can do this approximation, right? You know what I mean? Because how far is far enough? You know what I mean? You still probably cannot tell. If let's say 100 times away, of course you definitely find. However, only 5 times away, is far enough? You're kind of shaky, right? So how can we tell? Very safely tell. Safely and fairly tell. It's actually not that difficult. Okay. It's very simple. Just try what? Try two things. One is step response. Second is the frequency response. You say, okay, this system. Look at this system. You say this system. Okay, I'm using these two poles as dominant poles, and then I do the step response and frequency response, and then I do the step response and the frequency response to the original system, which has 3 poles, right? Compare these two. Are they close enough or not, right? They're close. Okay, the dominant pole method works. If they're far away from each other, then you can't do approximation. Then it's actually not very tricky. It's not very tricky. You just do a comparison. Yeah. Does it make sense? Any response, please? Still no response? All right, I have to go down then. All right, keep moving for this example 1. Okay, for this example 1. Giving the example 1 here. The question for this example 1 is actually asking multiple things. First question is asking to this system by using MATLAB. We will learn how to find original or uncompensated system through Locus, and from which find the closed loop poles. We are looking for the closed loop poles from the rule Locus rather than the mathematical calculation here. By the algebra, of course, you can find closed loop poles. Right? Second question is asking, find the corresponding what is this guy? Anyone remember? Anyone?
That the damping ratio?
Damping ratio. Here we go. Right, 2 is right. And 1 is, well, right too in terms of pronunciation. Zeta. Zeta. It's damping ratio. Now remember, damping ratio is something we learned for a second order system. Here we are approximating this third order system to a second order system. Here is saying if adding a PI controller AP as plus 0.1 over S, we're going to go into design any p-value to keep the same damping ratio zeta. See how we design the KP value to keep the same damping ratio for the system. Question 4 is find the step response for both uncompensated system and the compensated system. Find the step response also by MATLAB. Obviously, we're not hand sketching the time response. Okay, don't take it wrong. It's a MATLAB work. Like I said, it's about the final project. It's very close. Now let's see how to do this problem by using MATLAB. Okay. We still have some paper handwritten works to do and to clarify the idea. Okay. So the first procedure here is uncompensated system open loop transfer function is what? Because here the first question is asking for the original system rule locus, right? So what you need is the original system open loop transfer function. It's very easy, right? Denominator is just the 3 open loop poles, no problem. However, the numerator, what we should use here, remember, we're using constant 1. In other words, we are introducing a varying k onto the original 1. We're now using 72.3. Okay, so here, be very careful. We're using these transfer function, open loop transfer function, to plot the rule locus. So look at here, and then we go to the MATLAB. Oh, here I'm writing the code. I break the code into different sections. Okay, so the first section I give some kind of title and names, etc. Second section here highlighted by yellow. I'm clear all, close all, and clean the screen as well, okay. Without any other interferes from previously used data and the plots. And then I start to plot this open loop transfer function, rule locus. The easiest way to plot this, or say the easiest way to establish this transfer function is what? Because remember that the given is what? Closed open loop poles, -1, -3, and -10, right? Very easy to be identified. And do you have any finite open loop zeros? No, no zero, right? No zero. So you know the zeros and the poles of the transfer function. How to establish the transfer function? This way, right? This is called what? Zero pole gain. Zero pole gain function. Okay. This is something given in previous MATLAB slides. Okay. Hopefully, every one of you have reviewed those or learned something out of it. Okay. This is how you establish the transfer function. Okay, and of course here 0 is empty because no open loop finite 0. Right? Poles are what? 91, 93, and 9010. Okay, that's as given here. And then the uncompensated system, I name it as G1, right? Equals to 0 pole gain, 0 poles, and the gain of 1 here is 1. Remember, I mentioned you're introducing varying k into constant of 1. Of course, here I'm in the code we're not writing k. Okay, the k is varying numbers is injected by the command, this rule locus command itself. Right? And then rule locus is plotting the rule locus for the uncompensated system. This is the code, and if you run it, run at once, run this section, and this is the resulted rule locus. Uncompensated system rule locus. And the question is asking for, from this rule locus, we are looking for the closed loop poles. How to find this closed loop poles from this rule locus? Anyone knows? Any idea? This is go ahead.
Shouldn't that be the x-intercepts?
Intercept.
Like the -10, where the crosses are on the horizontal axis?
No. The cross on the horizontal axis are what? Open loop poles. Remember? That's how you plot the rule locus. Now we are looking for closed loop poles. How to find closed loop poles? Rule locus are parts of what? Closed loop poles, not open loop poles. Right? Open loop poles are the starting points we use to sketch the rule locus at the first place. Now we already have the rule locus from MATLAB. Now we are concerning the closed loop poles along the rule locus. So where to locate it? Is this concept clear? Anyone knows how we locate it? Anyone knows? All right, if no one, remember, going back to your original system, you have a gain here. I specified a gain here, 72.3. Okay, so this particular system is corresponding to a particular gain value, 72.3. Therefore, also corresponding to particular closed loop poles location along the rule locus. Does it make sense? Therefore, what we can do? We're moving along the rule locus until at a point showing the gain of 72.3. Now, what's the gain? Anyone can read here? What's the gain for now? 108. Good. So we obviously go down. Watch. And here there's a tip. Okay, it's very hard to locate the particular gain value. So what can we do? Zoom in. Okay, you want to do zoom in. So click here, zoom in, and then zoom in. Basically, because you know this is about this region, so you zoom in this region only. After that, close it, and then we start to find the 72.3. 72.3. Come on. 72.2. Well, this is the best I can do. Okay, this is the best that I can do. Makes sense. Of course, this one we need to delete. That makes sense. 72.2. Well, fair enough. 72.2. Fair enough. And also from here, from gain of 72.3, what do we find are closed loop poles of the original system? Who are what? Of course, dominant poles. These two are. Who are the poles? It's written here, 1.43 plus minus 2.64J, right? And if you have a little bit off, that's absolutely fine, okay, in the project. It's very tricky to locate exactly the point, okay? It's very tricky. You try, you know it. Okay. This is the question 1. Find the corresponding closed loop poles. Negative 1.54 plus and minus. Remember minus, okay, because the conjugate 2 pole, right? Plus minus 2.64J. And also question 3 is asking what? Damping ratio. So what's the damping ratio here? It's also labeled, right? It's nice. What is it? Off. 0.503. It's about reading. Now, after you understanding the concept, it's all about reading. It's become much easier. So you got closed loop poles and the damping ratio. Any questions before we moving on?
Why is it that we don't have a pole for the one that continues to infinity along the axis?
Of course we do, but we don't care. Remember, we are using the dominant pole.
I'm sorry, what was that? You're using the...
I'm trying to find it. Do this one more time. Of course, we have 3 poles, and those 2 poles are about here. 70, 73 something. If you want to locate this one here and then it's here, it's symmetrical about the x-axis. These 2 are the dominant 2 poles. Third one is along here. 73, right? 73, 72, I mean. Once again, it's very tricky. You need to zoom in this part to find 72.3. And you're seeing poles as what? Negative 10, negative 11, or say. Negative 11 comparing to negative 1.54 here. Around that is what? Far away. Much further than the dominant poles to the origin point, right? So approximation should work. Does it make sense? If you're looking for the third pose, yes, the third pose is here.
Okay, so we just ignore it because of the distance, right?
Yes, you can say that, but John is right, okay? Everybody, don't take me wrong. John was right. If you're looking for all of the closed loop poles, yes, you have 3 poles. This number is fixed. So 2 dominant poles here and here, right? The third pole exists. It does exist. You're looking along the third branch for the same number gain, 72.3. Then you locate that third gain. No problem. Okay, John was right about it. However, in this problem and also in our future design project, we are focusing on 2 dominant poles. Okay. The third pole is just used to verify that this approximation makes sense.
And what's the reason for? I I get that the frequency and radians per second should be present for the two complex conjugate poles, but why is it displaying a 10.9 frequency for the?
Well, anyone understand the real poles means what? The real poles means what? Real poles means what?
I know, like, are you saying like the real poles will automatically have some exponential without a cosine term? Is that what you're?
No, real poles means the system is overdamped, right? That's why damping ratio is 1. It's overdamped, actually. And there is no overshooting. Okay. Does it make sense? So it looks like a first order system. Right?
And why is it that there would still be a frequency present?
Frequency. Well, you still have frequency, of course. This frequency, it means nothing then. You don't even have oscillation.
Okay, so we just disregard the 10.9 frequency radians per second because
Correct.
It's not complex, right?
Correct. Your real pulse is not doing anything, actually. Real pulse not doing anything. Real pulse is not affecting or say dominating the performance of the system. No, it's not. It's a single real pole, or say a single real pole, therefore damping ratio is 1. However, if you think you have two different real poles, that's actually over damping. It's behaving like a first order system. It's not representing any, it's not even close to the real performance of the original system. No, the real pole, no. It's not showing, it's not presenting anything we want to see. Your frequency remains, but you don't even have an oscillation. Is it good to move on? All right, we can move on. What's the next question? We have done question 1 and 2. Okay, we got the ratio and closed loop poles. Third question is, if adding a PI controller, what do you see in this PI controller? What is a 0? 0 of what? 90.1, right? 90.10 is indicating a small 0, very close to the origin point. Remember at the beginning of today's lecture, what we are expecting to see what? After adding this PI controller, the locus basically remains same. We're expecting to see this because once again, your PI controller's 0 is close enough to origin point. Okay. If you verify this, but on the paper, we understand this. Okay. So after adding PI controller, which is Kp times S plus 1.1 over S, the compensated system looks like what? Looks like this, right? So once again, we are going to visualize this. Here is our added PI controller, right? This is the after compensation. This is a new system. Right? Question is asking for what? We are going to design the Kp value because Kp now is unknown. Kp obviously is unknown. We are going to design value for it to keep the same zeta, And what can we do? What can we do is the compensated open loop transfer function. And once again, we are doing everything via the rule locus, so we need to find the new rule locus, right? We are going to find a new rule locus, and we are expecting to see something basically same as before because of this zero, right? Because of this zero. And this time, how to find the rule locus? You're using what? This new zero is here. Old 3 poles remains, obviously. $72.3 and KP, the product between them is the new gain, right? However, when we plot the new rule locus, once again, we are neglecting them. We're not using any original gain. We're not using any original gain. And then go back to view, still be able to find KP. Okay, so how to plot the rule locus? Once again, introducing K directly to the system without any original gain there. Okay, so how to plot this new rule locus? Here. This is the code. In this section, what we are doing is adding a PI controller. Oh, Sawyer is right. Don't forget this guy. We do have a 0 pole. Very good. Thank you, Sawyer. Very good. Very good. We do have it. We do have it. Good. And then to plot this rule locus, first I'm defining the PI controller itself. Does this make sense? Numerator is as plus 0.1. Denominator is as. This is how I define them. And then the new open loop compensated system open loop transfer function is obviously the product between PI and original G1, right? Obviously, it's the product between them. And then I generate a new figure, blank figure, and then plot the new system rule locus. If I run this section, what do you see? First, very straightforward. You're seeing the rule locus is not changing much, right? It's not changing much at all. However, it's obviously not the same as before. See this introduced the new 0 here? Very tiny, very small, but it does exist. It's not exactly same as before, but it's not changing much either, right? This is justified the previous conclusion. Okay, PI can basically keep the original rule locus if you're designing your 0 close to 0, close to the origin point. This is a new rule locus. Anyone has any idea how to design the KP from here to keep the same zeta? How to find the KP?
Well, can't we just look on the complex poles to find 0.503 approximately, and then that'll be our gain?
Go on. Go on.
Wouldn't that be the gain then that we would have if we can find our
Very
point?
good. Very good. Very good. Okay. I hope everyone is following. John was right. Okay, well, John was right. What we do is, once again, locate a point. Locate the new closed loop pole point. This time is not by locating the gain, because the gain is the one we are looking for, right? What we know this time is not anymore. This time we know the zeta, 0.503, right? So we are trying to move along the rule locus to find that particular zeta value, right? Let's go. Okay, let's go. Where is it? What's the zeta now? Anyone can read?
We have to, the damping is 0.13. So we need to
Yep,
increase
yep.
our damping.
Yep, this question, just to make sure you know how to read this, okay? It's for now is 10.138. It's not the point we are looking for at all. We're looking for 0.503, okay, 503. 503. So obviously, what do you want to do? Once again, we need to zoom in, right? Delete this guy and zoom in. We know it's about here. We know it's about here. We just zoom in this area, right? After that, 503, right? No, too much. 50. Yeah, perfect. Trust me, it's not easy, okay? It's not easy. So, but I'm lucky enough to get it. Okay, now I got 0.503. See? All right. So what do we got? So from the compensated system through Locus, we can find the at zeta equals to 0.503. You can find the new gain, K prime, which is equals to what? What's the gain now? You guys read?
71.4.
Mm-hmm. Very good. 71.4. Okay, go back to here. Does it make sense? At this particular zeta, because this is the system, the problem required this particular zeta. So we go there, and then correspondingly rate what's the new gain at 71.4, right? And then therefore, what's the KP value? Anyone knows how to find KP from here? This is not KP, okay? This is not KP. This is K prime, the new system, total system gain, which is K prime here. This is 71.4. So how to find KP? Anyone knows?
Well, if K prime equals, go ahead.
Would we time 72.3 by a certain factor to make it equal 71.4? And that factor
basically Sawyer is right, but Alex's answer is precise and concise too, right? This guy equals what? Nothing but here, right? You see? Here we go. And from which we immediately find what KP. That's the 71.4 divided by 72.3. Whatever it is. It's lower than 1, but right? That makes sense. Take a look to see any questions.
So I got a couple questions. What would be the difference between just simply multiplying the control block from the PI controller to the plant? I'm assuming that's the plant. What would be the difference between just multiplying those and for K2, or sorry, K prime? Why couldn't we just put in 72.3 and then KP, and we would know that KP in this case is assuming the controller gain KP, right? Would we do that the same way?
Well, if you're clear on the concept, that's actually that actually works. I mean, the resultant Locus is exactly same, right? You know what I mean? Locus is exactly same. However, how you locate the point is different. You're not you're reading the value there. Do you understand that is a value of a product between these two, or directly the KP value? You need to understand that. If you do, then there's no difference.
Okay.
However, here I'm trying to differentiate the product between these two is not bothering your rule locus, first of all. Then after find total gain here, I'm very clear that the two are equal. And then from this equation, I derive the KP value.
Okay.
I consider this way is easier way for my students to understand, but if some of you understand it well enough, yes. It's not necessarily the only way. Yes, agree.
So going back to the question, probably one where it's just the plant model and the summation, why is it that we could get set different gains? When would we ever see that if we don't even have a controller or something to introduce that gain? Is this maybe something you would do separately? Like,
well, this PI is introducing new gain. Why not?
Yeah, but the system before, why is it that we would care so much about K changing? Because it looks like the system's like static, like where there's no value we're adding in, and we have to add a K just so we can see the root locus. Why, like, why would we want even to analyze the root locus if we knew that that was a static system? And are we assuming there's going to be someone's going to introduce some gain? Are we assuming that this is just a P controller?
Well, but the reason is you don't know if this given system is good enough or not. You don't know. Can you, by looking at this without sketching the root locus, can you know this system, say the damping ratio?
Oh, so this would be primarily to tell if it's unstable, right?
Not only stability, but also the transient performance. This is static. Yes, it is. It's not dynamic. However, you don't know how good it is, right? Can you tell those things by just looking at this block diagram? No way, right?
I mean, you wouldn't be able to without, like, why would you need the root locus in this case when you could just perform the Laplace of the entire closed loop transfer function?
Because can you further, if you find something wrong, can you further design a controller for it your way? Can you do that?
Oh, so like if we have something, if there's something, okay, we do the math and we find, okay, there's an unstable, it's unstable.
Yeah, what's the next step to improve it? So the title of this module is Design via the root locus, right? So this is I'm presenting how to use the root locus. Well, it may be not the only way, but this is one way. It's the focusing on the root locus and the play with it to deal with all of these issues. All right. Okay. We are going to move on. This is example one. Okay. It's basically touch base about the PI controller. It's not PID yet. And of course, the last problem, the last question, or say, is asking for what? Plotting both uncompensated system and compensated system step response, right? So that you're able to see the improvement. Right? Let's see the original system uncompensated system. The gain is K1, 72.3, which is given. After compensation, what is the K2? 71.4, right? Here is 6, but that's fine. Which giving you the damping ratio, the same damping ratio, 0.503. That's fine. Okay. And then this time to plot the step response, what transfer function you need? A closed loop, okay. So you got to be very careful. When you plot the step response, you're not using open loop transfer function anymore. It's closed loop. That's why I'm using this function as feedback, providing the feed forward and feedback transfer function inside of the parentheses. This command is looking for the closed loop transfer function. Closed loop transfer function for both, and then you plot the step response. By hold on, you presenting two-step response in the same page, right? Yeah, it's a very nice way to compare, right? And since you have more than one curve there, you need to have a legend to tell which is which. And by the way, inside of legend command, what this for? What this argument is for? Anyone knows? This number 4 is argument for what? This legend command is quite familiar, one we have been using for quite a while, but one of the argument is number 4. Anyone knows what is it? What? Oh, this 4 is indicating the location where you want to place your legend, which matter, okay, which matters, absolutely matters. Because if you're locating it at the wrong place, it can cover part of the what? Part of the result curve, right? Very bad, very bad. You need to choose the proper location to place your legend. Is a good design or not? Well, it's hard to tell. But here, what do you see is the improvement, right? What's the mistake here? Well, this command is not working. This argument. Well, let's delete it for now. Version MATLAB. Anyways, this location is good enough. So uncompensated system is, oh, the color becomes messed up. Here, blue and red. Blue is the original system. The red is the after adding the PI controller. First of all, the most significant improvement is what? Steady state error, right? So the blue has steady state error about what? About 0.3. Okay. The red has 0 steady state error. The effect are adding PI controller. Second thing is what? Your dynamics is not improved too much. I mean, original dynamic is even better, isn't it? The blue's dynamics, like the TR, TS, it's actually faster, much faster than the red. Right? So the PI is not governing a lot of the dynamic change. It's not. Especially you are placing your 0 close to origin point. You're not changing the, you're not helping the transit very much. That's, of course, exactly why we are going to learn what? PD. Okay. Does it make sense? All right. Any questions? All right. If this is fine, then let's talk about the PD a little bit and maybe leave the example to next lecture. The PD controller is the third one. First is the P itself, second is PI, third is PD controller. Okay. PD controller is like this. And if we organize it into the product between a gain and a zero, then we're seeing something like this, right? Right? This is the PD controller. And then what PD is doing is adding a gain, extra gain, of obviously, KP. Extra gain. Of course, when you design a PID, you want to differentiate the KP from PI and the KP from the PD. Okay, you need to be careful. These are not the same KP. Okay, they're not same KP. You have an extra gain out of PI, and you have another extra gain out of PD. Okay, they have different KP. Adding a gain here and a zero. A zero. And the zero's value is what? What's the zero's value? This is zero's value. Add a zero at this place. So here's the effect. It can introduce this zero in gonna change the Locus and compensated system Locus a lot, okay, or say significantly, zero. It really changed the Locus. If it can change the Locus a lot, that means what? That means you're able to improve the transit. Significantly. Remember previously in PI, we placed the zero close to a ranging point. Therefore, we're not going to be able to change the Locus a lot. Therefore, we didn't improve the transients a lot. We didn't improve the transient. Now we can use PD to achieve that. Of course, we're going to change the Locus a lot. This is what PD can do. This is what PD can do. PD can do. All right, we can stop here, and I will present the review for midterm 3, and you guys can take some notes. So midterm 3. Problem 1 is multiple choice. Okay, it's multiple choice. Okay, multiple choice. You have total up to 15 points to claim, and you might have 15 questions with 1 point per question, or you're going to have 10 questions with 1.5 point per question. Okay, this is the multiple choice. Remember to conduct these in the canvas, enter the canvas. Right? Problem 2 is our module 6. Is module 6 given a point to judge whether it is on the Locus? And if yes, what do you need to do? Anyone remember? If yes, what we should do? Anyone remember?
We have to find the gain.
Find the gain. Good. Find the gain. This is actually regarding what? Just apply 2 properties, right? Which 2 properties? Anyone remember?
The phase property and the magnitude property, right?
Here we go. We have examples. We have more than one example for this problem, so it should be fine. Of course, this is on the locus of what? Of a given system. The system can be given. The system is given. Judging if the given point is on the system's locus. This is problem 2. Okay. We have example out of module 6. And then problem 3. Problem 3 is actually also out of the module 6 is hence sketching rule locus. Sketching the rule locus. Here, first of all, you will only have real open loop poles and zeros. Okay. So that means what? Section 1 of the handout. That means you only need to worry about the section 1 of the handout, including like what? Anyone remember what involved in the sketching of the rule locus? What involved? To sketch rule locus, what do we have? Anyone? No one remember anything about it?
Is it determine the poles and zero on
And
the acetone and breaking point, whatever?
that's good enough. As long as you have some memory, that's good. Okay, so as long as you have some memory, that means you know which example you could go back to review, right? Good. This is problem 3. Problem 4. You're gonna do actually. This is something we haven't yet done, so just wait. Next lecture and lecture 20. Okay, lecture 20, which is on Wednesday. This Wednesday. It's actually doing what? It's actually doing even uncompensated system design PD controller to reach desired pair of dominant poles. Okay. It's on Wednesday. Okay, on Wednesday. We're gonna have such problem to design the PD. We also have problem 5. Problem 5 is, first of all, is extra credit. There's extra credit problem. Extra credit problem. If you don't have enough time or don't have enough interest, well, feel free to leave it. Okay. But if you do want to claim something extra, you want to do it. Okay. Extra credit. It's something about the rule locus. Rule locus. It's given a rule locus. Find and gains closed loop poles and also find what? Maybe also open loop poles maybe something also like even transfer functions, etc. So even a ruler can see how much information you are able to dig out. Of course, I have a specific questions. Okay, so not asking you to randomly throw out anything. No, it's not like that. I have a specific questions. It's all up to how much time you have and how much interest in you have. All right, any questions regarding the, oh yeah, the time. Same as previous exams. Okay, time same as previous exams. Same time length, same starting moment. Any questions? All good? All right. So thank you for attending today's lecture, and I'll talk to you guys on Wednesday, which you don't want to miss. All right. Bye now.